Welcome everybody to example 2. We are still looking at page 129 in the workbook here. And this is going to be our first example of maybe a little bit more of an abstract inner product space. Okay, so this time we're going to start with a vector space we haven't looked at in a while, the set of all continuous functions on the interval from 0 to 1. That's what that C01 represents. Okay, and in this example, our field of scalars is just going to be real numbers, okay? And here's our definition of the inner product in this vector space. Okay, the inner product of two functions, f and g, is just going to be the product, the integral of their product on the interval from 0 to 1. Okay, so I'd like to take a minute and see if we can prove that this is an inner product. Okay, which means we're going to go down the list of the 4 properties that an inner product has to have and confirm that this inner product has those. So we'll start with 3 arbitrary vectors, which in this case are functions and a scalar. Okay, and it turns out that all 4 of these properties kind of follow from calculus facts. Okay, so we'll start with A. We want to look at the inner product of f plus g with h, okay, and see if we can split that apart using that first linearity property. So by definition, that's going to be the integral from 0 to 1. Again, we're looking back at this definition. The integral from 0 to 1 of f plus g, that's our first function, times h. Okay, we look at that integral and notice that just using properties of real numbers, we can split that apart into 2 separate integrals, f of t h of t plus g of t h of t. Okay, and if you look at that, by definition, that's the inner product of f with h plus the inner product of g with h. Okay, so if you look at where we started and where we stopped, we have just proven property A in the definition of an inner product. So let's move on to B. Okay, so there we want to look at the inner product of cf with g. Okay, so by definition, that's going to be the integral from 0 to 1 of the first function, cf of t, times the second function, g of t. Okay, and then by properties of integrals, we can take that constant and pull it outside of the integral, and we're just going to get c times the integral from 0 to 1 of f of t, g of t dt. But that, by definition, is just c times the inner product of f and g. Okay, and looking at the beginning and the end, we have proven property B. Okay, so what about property C? Well, there we want to start with the conjugate of f and g. Okay, but here I want to make a comment. Or actually, I'm sorry, I miswrote that. We wanted to start with g and f. Okay, we'd like to show that the conjugate of the inner product of g with f is f and g, but remember that in this particular example, we are dealing with real numbers as our scalars. So complex conjugates don't really have any meaning in this case. If you take the complex conjugate of a real number, it stays the same. So we don't really need to write this bar here. All we really need to prove is that the inner product of g with f is the inner product of f with g. Okay, so let's start with this. By definition, that's going to be the integral from 0 to 1 of g of t times f of t. Okay, but we're just dealing with real numbers here, and so we can switch the order without changing the value of this. And by definition, that's just the inner product of f with g, so there really wasn't much to proving property C here. Okay, and then we come to the one property that's probably the most difficult to see, property D. Okay, and so there we need to start with a non-zero function and look at the inner product of f with itself. We're trying to prove that that inner product is something that's positive. Okay, so first of all, how is that defined? Well, by definition, that would be the integral from 0 to 1 of the product of f with itself. And I claim here that that is indeed greater than 0, but to really be convinced of that, we are using a real analysis fact. Okay, I'll show you what I mean. Okay, how do we know that that integral is really positive? Well, let's think about it graphically here. We're not going to prove that real analysis fact. This is something that you kind of have to build up your real analysis machinery for almost a whole semester before you can prove this, but here's kind of graphically why that's plausible. Okay, remember that f of t is a continuous function. That was the vector space that we started with. Okay, so f of t squared is going to have to be all non-negative values, so it's a function that's entirely up here, okay, where we've got positive output values. Okay, we made the assumption that f is not 0, so there's got to be at least one number in this interval between 0 and 1 where the value is not 0, and if you square that, it's going to be positive. Okay, so think about how the graph of f would have to look. It's continuous, and it has to go through this point where we have a positive value. So since it's continuous, it can't just jump up to that point. There's got to be kind of a gradual transition, meaning that the fact that that one point is positive kind of forces there to be some positive area under this curve. Okay, the continuity guarantees us of that, and that's why we can say with confidence that that's greater than 0. Okay, so putting that all together, we have proven that this rather strange way of thinking about an inner product as an integral actually is an inner product. Okay, and I want to give you just one example of a calculation just to illustrate what's really going on here. Let's pick two functions. Notice that they're both in our vector space. They're going to be continuous, so f of x is 1. That's just a horizontal line. And g of x equals 2x minus 1. What would the inner product of those two functions be according to our definition? Well, by definition, it's the integral from 0 to 1 of their product, so 1 times 2x minus 1. Okay, and if we do this integral, okay, we're just integrating 2x minus 1, so take our antiderivative, we're going to get x squared minus x. Evaluate that between 1 and 0, and what you discover is that you get 0. So we took the inner product of two functions and we got 0. What does that mean? Well, it means that these two functions are orthogonal relative to this inner product that we defined. Okay, and I think we have completed this example.